Okay, well, good afternoon, everyone. And yes, today we propose with my colleagues Jean-Benoit KOPP and Vincent Fournier. Vincent Fournier, who was the student worker of this experimental study, an analysis of something that is very common in the literature, which is a dynamic fracture analysis on Pmma. And in fact, so Pmma, polymethyl methacrylate, is a polymer material, but still is widely used to perform theoretical analysis to understand brittle fracture mechanics, especially in dynamic. And when I say dynamic fracture, I say that we want to plot, in fact, fracture properties like the fracture toughness or the fracture energy in dynamic, meaning that we want to plot this regarding the crack velocity. And we already know that these two material fracture properties are evolving regarding the crack velocity. And in the literature, as you can see on this picture, some people perform local analysis, some people perform global analysis, meaning measuring K or J, okay, using different kind of techniques, especially to quantify the toughness. So right now we saw works using photoelasticity, caustic methods, finite element analysis. And also they are using a lot of different geometry tests, okay? Finally, right now in 2024, if we want to have a global view of the material properties of a really simple material, Pmma theoretically has no heterogeneities, is mainly taken as a purely elasto-brittle materials. Well, look at this picture. You have a wide discrepancy. And in fact, it generates some problems, some remaining questions in the literature about the tendency, okay? If you take the red points, you say that, okay, it's a linear increasing revolution. If you take some other points, you can see some different phases in the increasing of the evolution. And also the relation between these points and these effects with local mechanisms due to the material response. And finally, also you have some inertia effects during the crack propagation that has to be taken into account in the measurements. So that's why, and when I said that also, I wanted to illustrate, of course, this one cannot be read exactly today or during this presentation, but we analyzed every work that we found very precisely to understand what was the formula that they used, what was the dynamic correction that they used, etc. What was also the value of the Young modulus and the Poisson ratio, because sometimes it is not exactly the same Pmma in 2024 or in the 90s. And we say that, okay, now we will try to propose another one, okay? But now, in this case, we will measure in the same time a local fracture toughness and a global fracture energy. And to do that, I will present the experimental setup that we use. So it's a strip bound specimen. The scheme explains to you the loading. Here you have some CAD illustration of our system. In fact, strip bound specimen test is well known to have few inertia effects, okay? And also can see an artificial crack initiation. And in our case, our system is made with a falling mass. Okay, as you can see here, the mass is falling, and then you have a razor blade inside the notch that trigger the propagation. And finally, we developed also a head-to-tail configuration. So in fact, you can see here on the back of the plate, you have a second one, okay? And these second plates, which do not break during the test, in fact, allow to have a really symmetric propagation and avoid to have some bifurcation. In this case, we try the most as we can to get what we call a quasi-permanent dynamic propagation. And before triggering the crack propagation, we perform a monotonous tensile loading and a relaxation, because Pmma, as I said, is a polymer material and is still a viscoelastic material. As you can see here, when we load our structure, if you wait for a relaxation effect, you can see that you have a small decrease of force. And then as we get the stabilized state of the material, we trigger and launch the crack propagation. Then we use DIC to get the local fracture toughness. And so then we apply a standard speckle on the sample. And we use an ultra-fast movie camera, getting us high resolution in time and space. So here is an example of the results we get. So you have here the end of the notch. And then we get a very clear, very symmetric and non-bifurcating crack at high velocity. So here you see 4 pictures of a 326 meters per second crack propagation. So now let's see how we perform the evaluation of K. Sorry, just let me check. Okay. So we use, as I said, a DIC method. So you have here the grid that we used to perform the DIC calculation. And then we use what is implemented in the code called U-Freckles Williams series. Okay. And thanks to the first order of the Williams series, we can get the fracture toughness. Okay. We also get the position of the crack tip. And adding to this fracture toughness, okay, well, in fact, here is the stress intensity factor, sorry. The stress intensity factor, we apply a dynamic correction, and you can have some details about this dynamic correction, but I don't have time today to explain to you. And here you have the results of the displacement field at the crack tip and around the crack tip, which is used to evaluate the Williams series coefficients and then finally get the stress intensity factor. With this analysis, we can get also, we can reach also to get high order informations at the crack tip and plot the T stress and the B stress all along the crack propagation. And these will not be used for the next slides of the presentation, but just can be checked that for every velocity, crack velocity and tests that we perform, these two quantities remains constant, meaning that we will have a quasi-permanent regime, meaning that no bifurcation appears to occur or branching. And finally, we have here on the left the stress intensity factor in mode 1 that shows an evolution with a plateau zone regarding the crack velocity. And here, the stress intensity factor in mode 2 that is always close to 0, meaning also that we have a straight horizontal crack propagation. And then finally, yes, sorry, we get the fracture toughness by averaging the permanent zone, the quasi-permanent zone. For the global evolution, sorry, there is a mistake here. And to get the energy release rate, the critical energy release rate, so the fracture energy, we use analytical function coming from the test, the SBS test. And then we apply also a dynamic correction. This dynamic correction is a function of the crack velocity and is get through a finite element analysis where we perform a generation phase analysis. So we apply the crack velocity as the input of the simulation. And you can see the trends of the function. Just for those who are familiar to this analysis, the famous Broberg formulation that is often used in the literature do not give you this tendency. It gives you a linear decrease from 1 to 1 here, and could be the source of some mistakes in the literature. Finally, the results. So as I said at the beginning, we just add new points to the literature. And you can see that we are in the same way, okay, in the same order of magnitude. But if you look only at our results, we clearly see three phases, okay? Limited by two critical velocities, Vc and Vm, and these two velocities are corresponding to local mechanisms. And we saw that very clearly by looking some fractographies. So here you have four different fractographies for four different tests. And you see that at low velocity, under the first value of critical velocity, you have a clear mirror surface. And then if you increase the crack velocity, you see more and more what is called in the literature conical marks. And when I say in the literature, in fact, we just are confirming only one paper from Dalmas and et al. That was already observed this kind of conical marks. And finally, we also compare these two values, local and global, by using the Irwin relation, but also with a dynamic correction. Okay, yeah, here. Okay, so you see the Irwin relation that we saw in the previous presentation, but adding a dynamic correction also. And we see that this relation between J and K is working very well in our case. And to our knowledge, it was kind of the first tentative to validate this function that I do not enter in the details, but which comes only from the work of Freund in 1950, and that proposed this dynamic correction. Okay, and these are my conclusions. I will thank you for your attention.